Chapter 44, Nuclear Structure. We begin our study of nuclear physics now, and we're going to finish it in two chapters, chapter 44 and 45. Nuclear physics is a branch of modern physics, and its importance is impossible to overestimate, not only because of its significance to our understanding of the physical world, but also because of the incredibly important practical applications. The nuclear industry, which is primarily how you harness the energy from nuclear reaction, is of pivotal importance in resolving the energy crisis that the entire human race will face in the near future. And what makes nuclear physics so incredibly important primarily is because of the energy that you can hopefully harness by nuclear reactions. And we know from Einstein's famous E equals mc squared equation, there exists a relationship between energy and mass. In chemical reactions, the mass changes very little. So therefore, we usually do not worry about any mass change. We just say there's chemical energy released during the chemical reaction, and that energy, if you convert to mass, is a tiny, tiny fraction of the total mass of the atoms involved. Therefore, we basically can use conservation of mass. On the other hand, in a typical nuclear reaction, there is a significant measurable change in the total rest mass of the system, and that corresponds to an energy change. So let's say if we change 1% of that energy, of the mass, and turn that into energy, that will be a tremendous amount, right? Because you have to multiply any mass change by c squared to get the corresponding energy that's involved. And that is typical in a nuclear reaction. We're actually changing the mass significantly, at least measurable change. So therefore, there is a lot of energy to be harnessed in nuclear reaction, and that is the primary reason why we study nuclear physics. In this chapter, we're going to mostly focus on the physics of the atomic nucleus. And in the next chapter, we're going to focus mostly on the industrial applications of nuclear physics, primarily the application in the energy industry. We're going to begin with a famous quote from the person who was probably most responsible for the birth of nuclear physics, because he was the person who discovered the atomic nucleus itself, and that person, of course, was Ernest Rutherford. Remember, he discovered atomic nucleus? Okay, what did he say? He said, nuclear physics, in his opinion, would never find major applications. Why did he still study nuclear physics? Well, to him, it was just for the purpose of understanding what's going on in the subatomic world. He was not concerned about actual industrial applications, and he wouldn't care even if there were no applications. He just want to know how the microscopic world actually looked like. But of course, we know today that the reality was just opposite to what he predicted. Nuclear physics is far from useless beyond academic research. It is one of the most important areas of our modern material civilization. Okay, so let's focus on the physics of the atomic nucleus in this chapter, nuclear physics. We're going to study these following basic aspects. First of all, we're going to start with basic properties such as the mass, the size, the density of the atomic nucleus, and then we're also going to zero in on the energy aspect of the atomic nucleus, so the so-called binding energy. We're going to talk about that. And just like the Bohr model, we can study the atomic nucleus by proposing nuclear models. And there are two famous ones that we'll be discussing here. And when it comes to atomic nucleus, one of the key features that we need to discuss is radioactivity. And that is actually most nuclei are not stable. They will decay into something else. It's called radioactivity. And this can be artificially induced, or it can also occur in nature. And we can even initiate nuclear reactions by bombarding the nucleus with something else. All of these things can lead to change in the nuclides. So those are the things we study in this chapter. In the next chapter, again, we're going to focus mostly on the energy aspect of the application of nuclear physics, and that is, how do you extract energy from nuclear reaction, especially neutron-induced nuclear reactions. And there are two primary things, but primary ways to do that. One is called fission, the other called fusion. We'll discuss the details. And in either case, we can put this physics to our use in drastically different manners. We can build a bomb, the atomic bomb, using nuclear fission, hydrogen bomb using nuclear fusion, or we can use the energy peacefully by building a fission power plant with nuclear fission, and hopefully in the not so distant future using controlled thermonuclear fusion to build a fusion-based power plant. And that, we believe, would lead to the final resolution of our energy crisis. We also study a little bit of nuclear radiation, how to detect it, and whether we can actually put it to good use, and so on. You know, people fear about radiation, but radiation, just like anything else in science, is a two-edged sword. Sometimes it's desirable, sometimes it's not. So we'll see how we can detect it and how we can put it to good use in certain cases. So that's an overview of what we're going to study in the next two chapters. Now, before we start our discussion of the basic property of the atomic nuclei, let us first of all clear out some confusing terminologies. I have written a number of terms that might be confusing. Nuclear, nucleus, nuclei, nucleons, nuclides, isotopes, isotones. Now let's see. Nuclear, it means having to do with the atomic nucleus. The atomic nucleus in singular form is called nucleus. In plural form, we do not call it nucleuses, we call it nuclei. Okay, this is just the plural form of nucleus. What about nucleons? A nucleus is made of nucleons. That's the constituent particles inside a nucleus. A nucleon is either a proton or a neutron. These are the two basic type of particles that you can find inside a nucleus. What about nuclides? Well, each nucleus, each type of nucleus has a certain number of protons and a certain number of neutrons. A nucleus with a given amount, given number of protons and given number of neutrons is called a nuclide. If you change either of these two numbers, you go to a different type of nuclides. Okay? And if we vary only the neutron number, but do not vary the proton number, then we have what's called isotopes. So you can have isotopes, basically, for example, with carbon, you can have isotope of carbon 14 and carbon 12. Carbon 12, 6 protons and 6 neutrons. Carbon 14, the radioactive isotope, has 6 protons and 8 neutrons. Different number of neutrons, but the same number of protons, so they get the same number of electrons as well, so they belong to the same element. These are called isotopes. What about isotones? Isotones are just the opposite. They share the same number of neutrons, but different number of protons. That's called isotones. Okay, so no more confusion. We have all these terms. With that in mind, let's start with our study of the basic properties of nuclei. Here is a symbol that we usually write for the atomic nucleus or for a given nuclide. X represents whatever element it is. Could be H for hydrogen, He for helium, and so on. A on the upper left corner is a so-called atomic mass number, sometimes simply called mass number. Z in the lower left corner is called the atomic number. Now you know what the atomic number is, right? It is the number of electrons in the element. It also equals the number of protons in the nucleus. The atomic mass number is the number of protons plus the number of neutrons. You remember, each electron, electrons are far less massive than protons and neutrons. Okay, the electron is about 1/2000th of the mass of a proton and the mass of a neutron. And the mass of proton and neutron are very close to each other. Okay, they're both equal to about 1840 times the mass of the electron. So basically, it is the nucleus that dominates over the mass of the entire atom. You can pretty much ignore the mass of the electrons as a good approximation. And since every nucleon share roughly the same amount of mass, it is the number of nucleons, whether it's proton, neutron, doesn't matter, that determines how massive this nuclide is. And so we have, so therefore A, which is the sum of the neutron number, Zn, and atomic number, Z, or proton number, Z, the sum, A equals Z plus N, is called mass number because that determines how heavy or how massive this particular nuclide is. Okay, so an example, that's carbon 12. Carbon, when we see carbon, it means C equals 6. Okay, 6 protons and 6 electrons outside. And it's carbon 12 because there are 6 neutrons in addition to 6 protons, giving you 12 total nucleons. That is an isotope, is a stable isotope of carbon. It's also the dominant form of isotope. The mass of proton in the conventional unit which we use in nuclear physics is MeV over C squared. Sometimes we only just call it MeV. It really means MeV over C squared. Okay, we usually do not use kilograms because that's too small. In kilograms, the mass of the proton is 938.3 MeV to 46 figures over C squared. Mass of the neutron, 939.6 MeV over C squared, is slightly more massive than the proton. You will see that later, why that's the case. And the mass of the proton and neutrons are roughly equal to each other, and it's about, again, 1840 times the mass of the electron. These numbers are good to know, okay? They're pretty close to 1,000 MeVs. So it's pretty close to 1 GeV. G means 10 to the 9. And so that's the mass. And we typically use, instead of MeV C squared, we use another unit for mass, which is even more closely associated with nuclear physics. It's called atomic mass unit. We saw that way back in Physics 1A. So here we introduce that again because we'll be using that as a standard mass unit throughout this nuclear physics discussion. 1U is defined to be 931.494 MeV per C squared. You see, it's pretty close to the mass of the proton and the neutron. Okay. By the way, when we say the mass of the proton, mass of the neutron, we mean the mass of a free proton and the mass of a free neutron. They are not locked up inside the nucleus. They are free. Okay. They're just there's nothing else nearby. It's just all by itself. So you see, 1U is very close to them, but a little bit less, right? It's 931, right? It's a little bit less. Okay, how did we find this 1U? Why do we choose this number to be 1U, 1 atomic mass unit? We take the most common form of carbon, which is carbon 12. Okay, this is carbon 12. And you know carbon 12 have 12 nucleons, right? Which is the dominant part of the mass of the carbon 12 atom. We can pretty much ignore the mass of the electrons. But since we usually deal with the mass of the entire atom, which includes its electrons, so it's better for us to take 12 grams of carbon atoms, okay, which includes, of course, 6 electrons per atom, per such atom. Each atom of the carbon 12 has 12 nucleons, so we take 12 grams of that has Avogadro's number in it, right? And what about if you look at each atom? What is the mass of each atom? The mass of each atom is 12 grams divided by Avogadro's number, right? Avogadro's number. And that will give you the mass of these 12 nucleons on average. Now you divide that by 12, what do you get? You get the average mass of the nucleons inside this carbon 12 nucleus. Of course, that is not quite exact because when we took 12 grams, that also included all these electrons outside, but that's a small correction. So basically, this number, this amount of mass represents the average mass per nucleon inside the carbon 12 nucleus. If you can ignore the mass of the electrons outside, which is a pretty good approximation anyways. You can see why it is a little bit less than those, okay? A little bit less than those. It's because these nucleons are locked up, right? There is an attractive potential that lock them up tightly together. So in order to liberate them, in order to break this thing totally apart into 6 protons and 6 neutrons far away from each other, you have to give it energy to break it apart. And when you give it energy, the mass increases. Okay, then the protons will become free and the neutrons will become free and they will gain a little bit of mass over that. So that's why. So you see here, as a first example, there is a measurable discrepancy in the rest mass in a nuclear reaction before and after. You see, if you are able to totally break that carbon 12 nucleus, on average, each nucleon will gain about, you can see here, about 7 to 8 MeV per C squared. That is just just a little under 1% of the total mass. That's quite a bit. So like I said, 1% mass change. That's to be expected as the order of magnitude in a nuclear reaction. No wonder people are so interested in nuclear energy, because there's really a lot of energy involved. Next, let's talk about the size or the radius or the diameter of the nucleus. How big is it? Well, the nucleus is very small. According to the initial Rutherford experiment, Rutherford took the alpha particles, whose kinetic energy is known, so we know how fast it moves with the speed v, right? And it's got a kinetic energy 1 half mv squared when it's very far away from the nucleus. Now, as it makes a head-on collision with a nucleus whose atomic number is Z, so it gets Z number of protons, there is an electrical repulsion between Z1, which is 2e, 2 positive e for the alpha particle, and Z2, which is the number of protons inside the nucleus. So there is an there is a positive repulsion. So the kinetic energy will eventually all turn into potential energy between the positive charges and positive charges, and that's when the thing stops and turns back, right? So there is what's called closest approach, and that is when the center to center separation is R1 plus R2, assuming it's alpha particle reaches here. So the center to center separation is R1 plus R2. We're interested in R2, the radius of the nucleus. So that's the conservation of energy approach. You can solve R1 and R2 if you know V initial for this alpha particle. You know Z1 and Z2. This is just Ke, a constant. You can actually find R1 plus R2, and from that you can estimate what R2 is. According to that those data, Rutherford found that the atomic nucleus is so small that the order of magnitude of its radius is no more than 10 to the negative 14 meters. Okay, this is no more, because if you had more energy, you could go even closer. You never know, right? It could go even closer. So therefore, this is only the upper limit according to Rutherford. Modern scattering data. Scattering means you have one particle, striking another particle. There's a collision. Modern scattering data show that the actual radius is even smaller. It's of the order of 10 to the negative 15 meters, which we call 1 Fermi. This term Fermi, 10 to the negative 15 meters, was invented by physicists. It is in commemoration of Enrico Fermi, one of the greatest physicists who ever lived, and one of the founding fathers of modern nuclear physics, Enrico Fermi, as in Fermi's Dirac statistics, or fermions. It's the same guy, okay? And it turns out that the size of the nucleus depends on the atomic mass number 8, which is the number of nucleons, okay, protons and neutrons. It turns out that, to a good approximation, R is equal to a constant times a to the power 1/3. That a is a constant which is about 1.2 Fermi. So roughly speaking, we're talking about 1 or 2 Fermis. Why a to the power 1/3? Can we say something about this 1/3? What does it really mean? Why 1/3, not 2/3, and so on? Well, again, a is the number of nucleons. Okay, number of nucleons. And if the nucleons are closely packed together, this is very different from the case of electrons, okay, outside. Electrons are very far from each other, but if nucleons are packed together with very little gap in between them, then we can say that the volume of this nucleus is pretty much proportional to the area, to the atomic mass number 8, right? Because you got 10 nucleons, which takes a certain amount of space. You get 20 nucleons, it takes double the space if you can ignore any gap between them. It's closely packed. And let's say this is spherical. If the volume is V, then the radius should go like it's related to radius like this, right? V proportional to R to the power 3, and therefore the radius should go like a to the power 1/3, right? Because a proportional to R to the power 3, and therefore R proportional to a to the power 1/3. So the fact that experimentally you get a to the power 1/3 really suggests that there is very little gap between nucleons. The nucleons are close together. They're closely packed together. Okay, they're so closely packed together that the density of the nuclear material is incredible. Let's look at nuclear density. Now that we know how big it is, and we know how massive it is, we can simply take mass over volume to find the density, right? So let's take a look at some numbers. Okay, so the mass is A times U, roughly speaking, because each nucleon has a mass about 1U. Okay, A is the total number of nucleons in the nuclide, so therefore it's A times U. Divided by 4 pi over 3, r to the power 3 is assuming it's spherical. But r to the power 3, r itself is A times, constant A times the mass number to the power 1/3. You can see here you raise to the power 3, and you have an A coming out. This A and A, that cancels out. Okay, so you know what that means? It doesn't matter how many of these nucleons we have. The density roughly remains the same. And that makes perfect sense because we're ignoring the gap between nucleus, between neighboring nucleons. And therefore, it's just a whole, just stack all of them together very tight. The density of the entire thing is pretty much the same as density of each nucleon, isn't it? So the number of nucleons, A, does not matter. Clearly, it doesn't matter here, okay? So we get that number. U, it's actually better to use in original kilograms. It's in this particular case, you don't use MeV or whatever because eventually you want to express everything in terms of kilograms, meter to the power 3, so you can compare with the densities we're familiar with, such as the density of water. Okay, so 1.67 times 10 to the negative 27, this is roughly the mass of a proton or a neutron. Divided by 4 pi a to the power 3, A is 1.2 Fermi, 10 to the negative 15 meters, and this is what you get. The order of magnitude of the nuclear density is 10 to the 17 kilograms per meter cubed. How does that compare with the density of water? The density of water is 1 times 10 to the 3 kilograms. So this is about 2.3 times 10 to the 14 times the density of H2O. 10 to the 14. We're talking about, we're talking about 2,300 trillion times the density of water. How bad is that? How bad is 10 to the 17 kilograms per meter cubed? Well, let's say I have a small piece of material, small in terms of size, okay? The size of a matchbox. A matchbox. But instead of a regular material, I stuff the entire matchbox with this kind of density, with, fill it up with nucleons, one next to another with essentially no gap. So I have a small piece of nuclear matter, the size of a matchbox. What would be the mass of such a matchbox? Let's see. We're calculating the mass m of a matchbox. If we're stuffed with nuclear materials with this density, okay, rho times v. Here's rho, right, 10 to the 17 kilograms per meter cubed. We're using only SI units, prime SI units, meter to the power 3. So this is the matchbox. Here we say it's about 10 centimeters long. Okay, it's about 5 centimeters wide, and it's about 1 centimeters tall. It's not much, right? So it's 0.1 centimeters. I'm sorry, 0.1 meters. 0.1 meters times 0.05 meters on this side, and then let's say 2 centimeters. It doesn't really matter that much. And what you're getting is 2 times 10 to the 13 kilograms. 10 to the 13 kilograms. We're talking about 20 trillion kilograms. Now, each ton, each metric ton is 1,000 kilograms, and 1 million tons would be then 10 to the 3 plus 10 to times 10 to the 6 will be 10 to the 9 kilograms, and this is therefore 20,000 metric tons. 20,000 million metric tons, I'm sorry. 20,000 million metric tons. Okay. How bad is 20,000 million metric tons? You know, we can build very large modern cargo ships to carry a lot of cargoes, right? But even with those very large ones, you would be hard pressed to find something that can carry more than 500,000 metric tons. Okay, you know, in comparison, the Nimitz class nuclear powered aircraft carriers each has a maximum load about 100,000 metric tons. So it's 0.1 megatons. 0.1 megatons. This is 20,000 megatons. So all these aircraft carriers, we only have, 12 of them, 11, 12 of them. We put them all together, we cannot carry something that big. If each ship can carry 500,000 metric tons, that's a huge oil tanker. How many of them would you need to carry something this small if it's all nuclear material? Will be, you can see here, 40,000 such ships. 40,000 subjects. I think it's more than the entire fleet of world combined. So therefore, the nuclear density is indeed incredible. Of course, you can argue this doesn't really matter because the nucleus is tiny, 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 and therefore you never have to do with something this big, right? It's filled with nuclear matter. Well, you would be correct if you limit yourself to this planet. But there are stellar objects, things out there in the universe. An entire celestial body is made of density like this. You may have heard about neutron stars. It's a star filled with tightly packed neutrons with this kind of density. An entire star. Think about that. So it's just mind-boggling to think about it. All right, so that's nuclear density. Now, we are really interested in nuclear energy, and let's introduce, therefore, a very important concept called binding energy.